The next problem we did in class together was the pumping station problem. And so I'm going to walk us through how to do this one. This one's a little more challenging than the other two problems we looked at. And that's partly because of the derivatives that we needed to take in the algebra manipulation that would be involved. So we're given a situation where we have two different towns and a river, and so they want to sort of figure out where we can put a pumping station, point S, so that we use the minimum amount of pipes to get from town 1 to the pumping station to town 2. And we're given some sort of distances between, and again, we're looking to minimize the length of pipe. So we're going to need to write a function that describes a length. Now, one of the lengths I'm going to be looking at is sort of this line I'm highlighting in orange, and the other one is going to be the line that I'm highlighting in purple. So let's start with the one in orange. If you notice right here, we have a mini little right triangle. And hopefully we remember from back in high school that right triangles, we can find side lengths within them using Pythagorean theorem, that whole idea of a squared plus b squared equals c squared, where a and b are the lengths of our legs and c is the length of the hypotenuse. So in this particular one, let's call this y. Length y would be our hypotenuse, and then one of our legs has a length of 1 mile, and the other leg has a length of x. So I could describe, I could use Pythagorean theorem to describe the length of y. I have 1 squared plus x squared equals y squared. Now, I want the actual length of y, so I'm going to solve this for y. So I would take the square root, and I'm going to replace 1 squared with just 1 plus x squared, and that would be the length of y. Now, I can't simplify that any further, so I'm just going to leave it alone. Now I'm going to head over and look at this other side length I need to find. I also have a right triangle. I'm given that one of the legs is 4, but I'm not given the length of the other leg. Instead, I'm given the total distance along the river between the two towns is 4 miles, and I know that this other piece was x. So I could describe this length right here as 4 minus x. So if I go through and use Pythagorean theorem now, I have my 4 squared plus 4 minus x all squared equals, and let's call this side z squared. And if I wanted to solve for the length of z, I would do the same thing I did over here. I'm going to simplify out that 4 squared. And for now, I'm just going to leave 4 minus x all squared. And I would take the square root of everything, and that would be equal to z. Now, the length of my actual pipe, so we'll call the length of the pipe p, would be equal to whatever the length of y is, plus the length of z. So let's go through and we're going to plug this in and make this a function of x. So our pipe length, p of x, would be equal to the square root of 1 plus x squared plus the square root of 16 plus 4 minus x all squared. And that would get me my length of my pipe. We're asked to figure out the minimum length. So just like all our previous problems, we need to know we need to figure out when the derivative is equal to 0. Now, in this particular function, I do have a restricted domain because there's limits on what x could be, since x is a length. So my domain in this case has to be a number bigger than 0, because I can't have a negative length, but it couldn't be longer than 4, because if it was longer than 4, we would be weirdly on the other side of town 2, and that wouldn't really make much sense. So my domain needs to fall between 0 and 4, which just means I'm looking for a critical point between those two spots. The other thing I sort of notice here is I might want to do a little bit of simplifying over here before I take my derivative, just to make my life easier. And so I'm going to expand this out And hopefully then my chain rule is a little easier to do. So I have 16 plus, and then if I distribute that, I'd get 16 minus 8x plus x squared. And I can simplify that a little because I have 16 plus 16, so I'm just going to save myself a little bit of writing and erase those and replace it with 32. Okay, I want to take a derivative. With derivatives, I also find it easier to rewrite my square roots as a group to the 1/2 power, because then I can use power rule. So I'm going to do the same thing over here. I can't combine these square roots because what's underneath them is totally different. And I'm going to go through and take my derivative. And I am not giving myself enough space, so I'm going to actually erase that and put p prime of x way over here. All right, I got chain rule going on here. So if you notice, I have an inner function and then I have an outer function. And when we do chain rule, a little reminder, chain rule is like if you have the f of g of x situation and I'm taking the derivative of that, I would take the derivative of the outside function with the inside function plugged in times by the derivative of the inner function. So here my outer function is that square root, so its derivative would be 1/2 1 plus x squared all to the negative 1/2 power. And then I'm going to times that by the derivative of my inner function, 1 plus x squared, which would just be 2x, because the derivative of 1 is 0, plus the derivative of x squared is 2x. And that then gets added, and I'm going to repeat the same process over here. So the outer function would be 1/2 32 minus 8x plus x squared to the negative 1/2. And the inner function would be negative 8, because this time I have this negative 8x term, plus 2x. And for now, I'm not going to simplify this. So I want to figure out where my derivative is equal to 0. So where does p prime of x equal 0? Now, it is possible to solve this algebraically, but for us, I really want us to focus on the calculus. So this would be a point in time where we might want to go to a Desmos graph and use the graph to get our critical values and do our derivative test. So in this case, if I pull up my graph of my derivative, and I already had it graphed and ready to go, I can sort of see the curve, and I click right here and I notice that I have a critical value at 0.8, and before the critical value, my derivative is negative, and after my critical value, my derivative is positive. So p prime of x equals 0 at x equals 0.8, and I can sort of show off my sign chart that I've checked. That value does fall between 0 and 4, and before that value my derivative p prime is negative, and after that value it's positive. So my function goes from decreasing to increasing. So yes, I have a minimum, which is what I'm looking for, that occurs at this particular point. Always go back and double check what you're being asked for. So we're being asked for the location of the pumping station, which we found, and the minimum amount of pipe. So we'd actually need to evaluate P of 0.8. And this is another instance where we could use our calculator to help. So I'm going to go back here to Desmos, and notice I already put in my P function. It's up here. A good check, you can look on Desmos like, oh, there's my, I'm going to shut off the y-intercept. There's my minimum value. It's at 0.8. And at 0.8, the output value was 6.403. So if I go here, I know 6.403. And I'm going to interpret my answers into a sentence. To minimize It helps if I spell minimize correctly. So to minimize the amount of pipe the station should be placed 0.8 miles along the river from Town 1. And we would need 6.403 miles of pipe. All right, so a quick review of what we did. We used Pythagorean theorem to sort of set up our functions to find the lengths, realized we had a restricted domain, did a little bit of simplifying, used chain rule to find the derivative of our length of pipe function, and then we needed to set our derivative equal to 0, and we solved that with graphing, and it did come out to be 0.8, and then also used the graphing calculator to evaluate the length of pipe to figure out that we needed 6.403 miles of pipe. All right, stay tuned for the last video on the final problem that we tackled during class, the snow cone problem.